So today we're going to discuss about the boundary condition, and this discussion is not only about the boundary condition but various type of boundary conditions available in the OpenFOAM. That is the basic idea behind this particular session. So when we are using OpenFOAM to find the approximate solution of a given equation, we are solving an initial boundary value problem. Okay, so we require the initial condition as well as we require the boundary condition to create a well posed problem. Okay, so for that, boundary condition play a very essential role. In this initial boundary value problem, we need to impose appropriate boundary condition as well as initial conditions. Okay, so as now you all know how to specify initial conditions. So initial condition straight away goes in the zeroth folder. Okay, so we have a couple of options. Either we go with a uniform type of initial condition, or we go by non-uniform type of initial condition by going with some type of the map field type of the options. Okay, so if we use the utility map field, then it goes toward the non-uniform type of the initial conditions. Okay, boundary conditions are a required component, okay, of the numerical methods. They tell what is going on the boundary of the domain. So let's say we are talking about fluid flow through a channel, so we definitely require at one place the inlet condition and one place at the outlet, and let's say it is a channel, so maybe let's say bottom is the wall and the top side we specify the slip conditions, like atmospheric type of conditions. Okay, along with that, initial condition also required component of the numerical method. They define the initial state of the problem. Okay, so normally if we are working towards the, let's say, steady state type of the calculations, okay, at that point of time these initial conditions play bigger role. Okay, if we specify very nice initial condition, then maybe the convergence is very fast. Okay, but when we working with the transient simulation, this initial condition is not matter a lot. Okay, why? Because after a first iteration, the or first time step, that is going to be wash out more or like. Okay, so that's why when we are working the steady state type of the simulation, this initial condition is very important aspect. Okay, so let's look at few basic things in terms of OpenFOAM. So OpenFOAM distinguishes between base type boundary condition and numerical type boundary conditions. Okay, so this base type conditions is something like patch, wall, symmetry. So there is a two type of base type condition if you look at. So unpaired and paired. Okay, so unpaired, that is a patch and wall, very simple base type conditions, and in pairwise, that means symmetry, empty, wedge, cyclic, and processor. That goes as a pair type of conditions. Okay, so what is base type and numerical type? There is a difference. So whatever we are going to specify inside the polymesh directory inside the boundary file, that goes as a base type. Okay, and whatever we are going to specify in the zeroth folder, it's called the numerical type of conditions. Okay, so when we say, let's say, unpaired and we specify, let's say, wall. Okay, so on the wall we are going to specify, let's say, either fixed value for velocity or zero gradient for pressure. Okay, and when we specify, let's say, patch type, so either with the patch type we specify, let's say, fixed value as well. Okay, as in for velocity. Okay, as well as at the outlet, if we specify the patch, then it goes as a inlet outlet condition, zero gradient condition, total pressure condition, fixed uniform type value type of conditions, and all this thing. Okay, when we talk about the pair condition, what it means, if you specify at the base type, let's say, empty, the same pairing supposed to go at a zeroth folder. If you specify symmetry, so at the same location in the zeroth folder for all field variable, it goes as a symmetry conditions. Okay, if you specify cyclic at a boundary file, that must go cyclic in the zeroth folder. Okay, so like that way it is a called the pair condition. And unpaired, you specify the patch and you have multiple selection, you specify the wall, you have multiple selections. Okay, so that's why it is called unpaired type of conditions. Okay, base type condition, as I told you, are defined in the file boundary located in the constant polymesh. Okay, the file that is located in constant poly folder, it is created when you create a mesh. Either you go with the block mesh file, when you execute the command block mesh, then that particular file is created in the poly constant folder under constant polymesh, and inside that there is a boundary as a file. Okay, or you can import the mesh either with the let's say import utility, like if we create a mesh for a Fluent, you can import the mesh like a Fluent mesh to form, and when you apply that command, you will see additional file is created inside the polymesh polymesh directory. Okay, so that is why it's called the location where you can find out this boundary file, and inside the boundary file we're going to look at the base type of conditions. Okay, and the numerical conditions or numerical type of boundary condition you can see in the 0 directory. Like in the 0 directory, if we are simulating only fluid flow problem, then we have a U and P as a 2 file. Inside that we have a chance to specify numerical condition in the 3 way, either Dirichlet condition. What is Dirichlet condition? Simply we are giving the fixed value condition, like fixed value for velocity, so or fixed value for pressure. It's called Dirichlet condition. So when we are specifying wall for at that point of time, also for velocity it goes as a Dirichlet condition. Newman condition, when we specify the gradient of any quantity, it's called Newman condition. Robin condition or mixed condition, mix of both of them. Okay, so it's called the Robin or mixed condition. So in the OpenFOAM we have a different type of options available. Okay, primitive and derived type of conditions. Okay, later on we explore that part. Okay, so name of the base type boundary condition and the name of the numerical type of boundary condition need to be same. Okay, so what it means, in the base type condition is available a constant poly boundary file, so boundary name supposed to be same. Here you have inlet, so you must have an inlet entry in 0 and P folder. If you are top as one of the name, you must have an entry in 0 and P folder. If you don't have that same entry, whatever the entry available at the boundary file, same entry is supposed to be available at a 0 folder in all the sub files, but it not reverse. Let's say you are working with different type of problem and you have more number of boundary name or boundary patch conditions is available in 0 folder, and same name is not available in the boundary file, no worry. Okay, but reverse is not true. Whatever is name is available in the boundary must available inside this particular 0th folder all the files. Okay, so please remember that, otherwise OpenFOAM immediately give you the fatal error that this patch name is missing. Okay, inside the boundary file. Okay, so following type of boundary condition goes as a paired, as I told you. Okay, so what it mean, if you specify in the boundary file as a symmetry, so 0 folder for all the variables is must goes as a symmetry. If you specify symmetry plane, it's supposed to be symmetry plane. When you are working with the 2D, it is empty condition in the boundary file, it must goes empty inside the 0 folder. So it is called the pair type of conditions. Okay, so one has to take into account. And when we talk about the numerical conditions, okay, so for numerical condition, if you specify the patch, okay, so in the boundary file you can choose either of any of these options. Okay, either fixed value, fixed gradient, 0 gradient, fixed flux pressure, inlet outlet, free stream, sleep, total pressure, uniform fixed value. Any of this condition you can choose. Okay, for 0th folder. So please understand, when we want to specify the boundary condition, we have to think about 2 places. One is constant folder inside constant polymesh, and inside polymesh we have boundary file. So we must have a proper name of all the patches inside the boundary file as well as type inside the boundary file. In the similar line, we have to think about 0th folder. Okay, so we must have a one-to-one mapping immediate from patch from the boundary file towards the 0 folder. So let's quickly look at that aspect. Okay, so we not going to mess up here. So let's go towards any of the tutorial. Okay, so let's say piezo form, RANS modeling. Okay, let's say we are working K omega model. Okay, and let me show you the polymesh directory boundary file. Okay, so polymesh directory boundary file contain 3 name. Okay, moving wall, fixed wall, and front and back empty. So moving wall type is wall. Okay, so this type is wall, fixed wall type is wall. Okay, now let's go towards the 0th folder. Okay, so in the 0 folder you open any of this file. Okay, for each one of this file you must have all these 3 name. That means whatever the name is available here, moving wall, fixed wall, and front and back, similar names supposed to be appear here in moving wall, fixed wall, and this. Whenever you specify at a boundary as a wall, you can choose either fixed value or gradient. Okay, so we have a option fixed value or gradient. Okay, so like that way you have a one-to-one mapping. Let's go towards other folder. Okay, let's say this T junctions. Okay, in this, if you look at the polymesh, one of the boundary file. Okay, so in here you have a inlet, outlet 1, outlet 2, and default faces. So we have a total 4 patches. Okay, and all we inlet and both the outlet specify as a patch type, and here default wall, that is surrounding wall, goes as a wall. Okay, so in the similar line, if you go to the 0th folder of this particular test case, okay, if you open any of this folder, we must have that 4 entry, that is inlet, outlet 1, outlet 2, and default. Okay, so if we go towards this, here we are specifying a different class of conditions. Okay, so but this condition goes very well with the patch type of conditions, or patch type that you specify as a base type of boundary condition in the particular boundary file that is located in constant polymesh folder. Okay, so this is base type. Okay, whatever you specify in inside the polymesh directory inside the boundary file, it called the base type, and whatever is specified the 0th folder in either of any of this file, it called as a numerical type of conditions. Okay, so that is difference in between these two things. Okay, so when we specify the wall, as I told you, okay, we have a for velocity we have fixed value. Okay, so type fixed value you specify uniform 0, or for pressure you specify the gradient conditions. Okay, so like that way you can specify this class of conditions. This boundary condition is not contained in the patch base type boundary condition group. Okay, because specialized modeling option can be used on this boundary type of the conditions. What it means, we cannot specify as a patch condition and apply this fixed value and all this thing. It goes wrong. Why? Because sometimes we want to look at, let's say, near wall modeling, like turbulence modeling. At that point of time, this wall M is essential. Okay, so that is what it means. We cannot specify patch and do this type of or we specify the patch and we go with this class of boundary condition inside the 0 and P folder. Okay, so wherever the wall condition must be attached with the geometrical configurations. Okay, but patch condition is not going to be attached with the geometrical condition. Why I'm putting this word? Let's say we are talking about flow over circular cylinder. Okay, so circular cylinder geometry is the definite geometrical configuration, and so we must specify wall condition over the circular cylinder geometry. But inlet, outlet, top wall, bottom wall is the fastidious condition. So to facilitate our simulation, we are specifying certain patch, so it goes as a patch type of conditions. Okay, same way, let's say flow through a pipe. So inlet and outlet, okay, it is called the fastidious or the patch type of the geometry, but the surrounding walls of a pipe is the geometrical configuration, so it must goes as a wall conditions. Okay, so there is a particular difference between wall and patch. Okay, so wherever the information we have to take into account from the exactly geometrical configuration, it must goes as a wall type of conditions. Okay, where we want to specify certain later on certain modeling, like turbulence modeling, heat transfer and phenomena, anything. Okay, so at that point of time, that is very essential. Okay, so if you look at the broader patch attribute, it we divide something like this way: base type. So in the base type we have a patch and wall. Okay, that is unpaired, and otherwise as a paired type, symmetry, empty, wedge, cyclic, okay, periodic, all this goes as a base type. And when we specify the patch type, at that time we have a numerical condition. In the numerical we have primitive type and derived type. Okay, so both come under the numerical conditions only, numerical type only. But primitive type we have a fixed value, fixed gradient, zero gradient, mix, directional mixed or calculated. It goes under the primitive type. And derived type like inlet, outlet, okay, oscillating, time varying, all these come under the derived type of conditions. Okay, so there is a segregate groups of boundary conditions. Okay, so now I think you understand. Base type, this portion or this entry is supposed to go inside the constant folder polymesh. Inside the polymesh there is a boundary file. Inside that is this entry supposed to go. All this entry, primitive or derived, that means numerical type, it's supposed to go in the 0th folder. Okay. So base type, the type of the patch described purely in terms of geometrical or the data communication links. Okay. So as I told you, it is completely linked with the geometrical configuration. The base type condition is type condition supposed to specify at a poly mesh level inside the boundary file. Okay. Primitive type, the base numerical patch condition assigned to the field variable on the patch. Okay. So base numerical conditions, that means fixed value, fixed gradient, zero gradient, mix, it's called the base numerical type of the patch conditions. Okay. And derived type, complex patch condition derived from the primitive type. Okay. Either derived from the fixed value, derived from the gradient, derived from the mixed type of the primitive type. So that goes under the derived type of the conditions. Okay. And it is also assigned on the patch type of condition as a base. Okay. The numerical patch type, be in a primitive or a derived type, is specified under the type keyword of each patch in the field file. Okay. So what is that mean? That mean, if you look at here, this is field file and this is the name, numerical name of that inlet, outlet. Inside the field variable, this is supposed to be specified at that level. Okay. So if we don't specify this, then OpenFOAM immediately give us the warning sign that something is missing at so and so locations. Okay. So that is what one has to take into account. Okay. Now geometrical patch type, if we look at, okay, so geometrical patch type or base type we look at, then we have a certain options like patch generic type containing no geometrical or topological information about the mesh, used for an inlet or outlet type of planes. Okay. So patch type, it is not directly attached with the geometrical configuration. At that point of time we go as a patch condition, and on the patch you have different option, go with the inlet outlet type of the conditions. Okay. Wall, for patch that coincide with the solid wall required for some physical modeling like heat transfer, wall function applications, for turbulence modeling, all that purpose, this wall particular class of base type condition supposed to be mentioned on so and so boundary inside the boundary file. Okay. Symmetry plane, for a planar patch which is symmetric plane. Let's say we are talking about the flow through a pipe. Okay. And let's say we are talking about, let's say, two-dimensional analysis of flow through a channel, let's say, and so or flow through a duct. Okay. So if our flow physics is laminar, in that case it is not required that we go with the entire two-dimensional portion. We create a half portion through the axis. Okay. And we either work with the top half or the bottom half, and like that way we can specify the symmetric plane boundary condition at the where the axis is cutting the particular plane. Okay. So that is what it's called, the symmetric type condition. Wherever you have a physics also symmetric as well as geometrical similarity is there with respect to any of the plane, at that point of time the symmetric plane condition normally people use. Either let's say sometime we are talking about, let's say, flow through a bundle of this tube bundles. Okay. At that point of time, even though you have symmetric, but we cannot specify symmetric, that point of time we require the cyclic type of conditions. Okay. Because we have so many number of tube bundles in it. Okay. So one has to check and judge appropriately which condition one has to apply at what locations. Okay. Symmetry is more generalized class of these conditions. So for any non-planar patch which use the symmetric plane. Okay. So whenever we specify symmetry or symmetric plane, it all immediately apply something like a slip type of conditions. Okay. So for a non-planar patch, if we are talking, then we go towards the symmetry. But if we know that whatever the patch on which we are going to apply symmetric condition is the planar patch, then go with the symmetric plane type of condition. Empty, now you know, for solution in 2D or 1D dimension. Okay. Where we don't want to simulate in the other directions. Okay. So at that point of time, in that particular direction we apply the empty as a conditions. Okay. Then wedge, so for a two-dimensional axis symmetric case. Okay. So let's say this is, we are talking about flow through a pipe and we want to only simulate this 5 degree small segment of this circular pipe, then we go with the, let's say, wedge, small portion of wedge, and on this 2 patch we apply the wedge condition. Okay. And we have axis of symmetry, and we have inlet and outlet. So it is very good options when we are talking about the circular geometry, cylindrical pipe, or any class of this thing. At that time we go with this wedge, so it will facilitate us the axisymmetric type of calculations. Okay, cyclic enable two patch to be treated as if they are physically connected. Okay, used for separating geometries. So as I told you, let's say we are working with flow through a tube bundles. Okay, at that point of time we can apply the cyclic conditions and we can reduce the solution of number of tube bundles. So whoever working in this heat exchanger type of simulation, they don't want to simulate entire number of tube bundles over which the flow is passing. Okay, so otherwise it's too heavy to simulate. So for that purpose people go with this cyclic type of conditions. Okay, one cyclic patch is linked to another through a neighboring patch keyword in the boundary file. Okay, whenever there is a cyclic condition is supposed to match 1 to 1. Other way to look at the cycling condition is something like this way. Let's say flow through a very long pipe. Okay, so we are interested to look at its fully developed nature. Let's say laminar pipe. Okay, so either we construct very long pipe and try to simulate, or in the streamwise direction we can create a very, let's say 1 meter long pipe only, and in the streamwise direction we apply the cyclic condition. But when we apply the cyclic condition in streamwise direction, we have to change the code, because then the pressure loading goes as a source term inside the Navier-Stokes equation. But when we are doing that way, that means inlet and outlet, it's now cyclic. What it means, the whatever the flow is going out, immediately it going to enter in the next portion of the 1 meter size pipe through the inlet. So what going to happen, whatever going out, that immediately enter through the inlet. So like that way it's inlet to so outlet to inlet, we have a complete map. So for that purpose we require the neighboring patch keyword in the boundary file. Okay, so whenever we going with the cyclic condition, as at that point of time we have a patch neighboring connectivity required. That means whatever is going out, that must enter inside the inlet patch. So that's why you will see this neighboring patch keyword as extra entry inside the boundary file. Okay, so when we try to simulate one of the case with the cyclic, you will come to know how exactly it's going to happen. Each pair of connecting face must have similar area to within the tolerance given by the match tolerance keyword. Okay, so normally what happen, whatever the inlet area and the outlet area, that's supposed to map equally. Okay, what it means, let's say we have a convergence divergence sections. Okay, and in that case it's very long convergence divergence section, so we cannot at that point of time apply the periodic condition. Why? Because now if you look at the inlet and outlet portion, it's, if we look at the area, it's completely changed. Okay, so at that point of time it is not the good way to apply the cyclic conditions. Okay, so whenever you have a you want to apply the cyclic condition, you have to look at the patch area for neighboring patch and the current parent patch supposed to be mapped within some matching tolerance. Okay, so we cannot violate that part. So that is one thing. Okay, then we have a cyclic AMI condition, like cyclic but for a cyclic only but arbitrary mesh interface. Okay, AMI, that means arbitrary mesh interface, that is its full form. Okay, cyclic arbitrary mesh interface. Okay, that is a very good conditions. Okay, where two patch whose face are not matching. Okay, so as I told you, in the cyclic, two face supposed to be matched, but if you have a some case like rotating geometry. Okay, so in that class it not necessary the stator and rotor both have a similar type of the matching patch. Okay, at that point of time you can apply this cyclic arbitrary mesh interface. Even people go with cyclic arbitrary mesh interface type of condition if you want to merge two type of the mesh. Okay, let's say you constructed the two type of the mesh from different type of the mesher. One is unstructured and the structure. So this cyclic AMI or arbitrary mesh interface goes very nicely. Okay, in that regard. So that is how you can see the or you can map the two different unmatched type of the patches with the help of the cyclic AMI. Processor type of boundary condition or type is normally goes with the interprocessor connection boundary when we are working with the parallel computing environment, at that point of time when we do the domain decomposition, or we use the decompose type of the utility to decompose any of our domain, at that point of time when you look at inside the each processor folder field information as well as boundary information, at that point of time you come to know about this processor level type of boundary conditions. Okay, so we also try to look at when we start parallel computing type of calculations. Okay, then so we have a different class of primitive type of boundary conditions. Okay, so this is all various primitive class of boundary conditions. So fixed value, so this primitive class of condition goes with a patch type of conditions as well as wall type condition as well. Okay, so if we specify the fixed value as a type, okay, so this type you have to specify where in the 0th folder, this all is the type. Okay, this all called is type. So if there is a primitive type, then this is the options available. Okay, you have, so primitive you have a fixed, you have fixed value, fixed gradient, zero gradient, calculated, mixed, and directional mixed. Okay, so fixed value you can specify directly the value. Fixed gradient you can specify the gradient. Let's say we want to specify the heat flux condition. Okay, for the temperature heat transfer phenomena, either you specify the constant heat flux or constant temperature. Constant temperature quickly goes with the fixed value, constant heat flux then we have to rely on this fixed gradient type of conditions. Okay, zero gradient, that means the normal gradient to the that particular normal gradient of any of the quantity phi on that particular patch is goes to 0. Okay, calculated, boundary field phi derived from other field. Other field, that means internal, sometime internal field, or sometime we have a directive so that we can calculate based on the other field as well. Okay, mixed value or fixed value type of conditions. Okay, so for that like a inlet outlet, it's something like a mixed type of conditions. Okay, because if the flow is going out, then it appear as a fixed zero gradient. Okay, or if flow is reverse flow, then it goes a fixed value. Okay, so that is how you can see something like a mixed type of conditions. Okay, reference value, reference gradient, volume fraction value, depending on where you are applying mixed, some different data entry is required. Okay, direction mix, a mixed condition with a tensorial volume fraction for different level of mixing in normal and tangential directions. Okay, so this come under something like a how the tangential and the normal component portion are mixing. Okay, so for that also we require the reference value, gradient, and volume fraction, and few values entry we required. Okay, so let's look at certain class of the derived type of conditions. Okay, so derived class of condition that we normally going to encounter is inlet and outlet conditions. Okay, which switch between zero gradient when the fluid flow out of the domain. Okay, so if fluid is flowing out of the domain, okay, so normally we specify this condition at the outlet. So if the fluid is flowing out of the domain, then we consider it as a zero gradient. Okay, and fixed value when the fluid is flowing into the domain. Okay, so when fluid is start entering within the domain, then we say fixed value, and that fixed value goes with the inlet value, this particular value. Okay, if we set 0, then fixed value equal to 0. If we specify certain fixed value, with that it allow the flow to enter from that reverse flow type of the place. But when we apply the inlet outlet, you have to understand by default goes as a gradient until unless from that particular patch some reverse flow is happening. At that point of time, whatever the value is specified, it goes with that. Okay, so another class of condition is called the proper entrainment type of boundary conditions. Okay, so entrainment type of condition, that means it's allow the flow to enter freely from that particular locations. Okay, or allow the flow go out of that boundary freely. Okay, without any resistance. So combination goes very nicely, something like a total pressure conditions on the pressure side, and pressure inlet outlet velocity on the velocity side. Okay, so that is how this two pair goes very nicely. So total pressure conditions, so for an outflow it's pressure equal to 0. For an inflow, pressure whatever is specified, okay, it goes something like this way, and from this one can calculate what is the velocity at that particular inlet patch. Okay, the pressure inlet outlet condition specifies zero gradient at all the times except on the tangential component, okay, which is set to fixed value for inflow. Okay, so what it mean, that means whatever the tangential component, let's say flow is entering inside the in the two-dimensional, let's say, channel from left to right. Okay, so if flow is entering from left inlet wall, so we have x component and the tangential component is, let's say, y component. So it's always apply gradient to the x component, okay, except the tangential component. That means if 2D, then tangential component is what, v component. Okay, so v component always goes to 0. Okay, so like that way it try to mimic the change with the help of the pressure inlet type of the conditions, and they try to look at the incoming velocity based on the total pressure, these conditions. Okay, like that way that we able to fix the entrainment class of conditions. So it allow the flow to enter very freely from the inlet portion. Okay, so that is how you can see, like if you look at the same page, total pressure, okay, P0 entry goes 0. If you have some pressure driven flow, then specify what is the pressure at that location. Okay, or and at the velocity side you specify simply this entry, pressure inlet outlet velocity. Okay, and it goes very smoothly with that particular class of conditions. Okay, then you have fixed flux type of pressure condition. So this condition is normally based on this zero gradient condition. So it's normally used for a pressure in the situation where zero gradient is generally used. So in the situation zero gradient generally used for pressure, that means wherever you specify the velocity as a distillate condition, normally at that portion pressure goes as a gradient condition. Okay, but in the calculation some body force such as gravity, surface tension is available. Okay, at that point of time, it's as compared to zero gradient, try to apply the fixed flux pressure. So it try to take into account this additional forces while they are calculating the pressure near the wall. Okay, so that's why normally when we go towards Boussinesq type of calculations, okay, at that point of time you can see as compared to the zero gradient, you will see for pressure always people go with the fixed flux type of the pressure condition as compared to the zero gradient type of conditions. So it's almost behave as a zero gradient only. Okay, but it try to take into account certain quantities like gravitational forces and surface tension forces. Okay, then sometime we have to rely on some time varying type of conditions. Okay, so time varying type of condition, there is a uniform fixed value. So total pressure fixed value, oscillating fixed value, pressure fixed value. Okay, so uniform, in place of uniform certain other name it's going to appear. Okay, so with the help of that you can find out what different options is available. So for that we have a, let's say, uniform fixed value. You can specify certain constant value with which the flow is entering. Okay, then you have a uniform fixed value in the table form. Okay, so what it means, it's going to start from 0. Okay, and it's going to reach till 10 second, and during that time it try to interpolate between 0 to 2 as a velocity, as a pressure or velocity. This is about the scalar part. Okay, so like that way you can see. Then you have a leverage to specify through some data table. Okay, so you can specify the text file. So if let's say you need not to write like this way, then create certain text files. Okay, let's say we have a 0 to 1 second, we have other value, from 1 to 2 other, 3 to 4 other. Either you write it down here itself or try to go with this type of the data table. Okay, so either of that way you can specify. Okay, so like here you have fixed value uniform with you have a CSV file also. Okay, so few more entries it's available, header line, some reference coefficient, component column, data column index. Okay, separator, so how the data is separated from one to other. Okay, so these few entries is available with the help of this uniform fixed value class of the conditions. Okay, if we are going with something like oscillatory type of the things, then we have a frequency, amplitudes, and scale and level. Okay, few more factors is appear. So this is and here we have a square type of the wave, or this way you can specify different things. Okay, so time varying boundary conditions has certain options. Okay, but I normally don't go with this options. Okay, if I want to specify the time varying some equation or something, then either we go with the groovy BC type of the conditions that is available in Swank form, or best part is code by our own boundary condition and go ahead. Okay, so with the help of that we have a proper flexibility, okay, to control our own way of inflow, outflow, or whatever the dependent variable, how you want to vary everything. We can very quickly, let's say we want to see this our incoming velocity is a function of sine, and sine is 2 omega t. Okay, inside the sine we have a 2 omega t. So if that class of condition we are expecting, then it's best way to code ourselves or go with the groovy BC type of the options. Okay, then let's say we have polynomial fitting type of the condition you require, then also you can go very quickly. Okay, so 1 0 2 2. Okay, we have it is so that means t to the power 2, t to the power 0 3, like that way you can increase the polynomial. Okay, like that way you can specify different type of the time varying type of conditions. Okay, so depending on your requirement, either you go with the uniform fixed value or you can code it by your own. Okay, so when we go with this uniform fixed value, we have a certain options. Either we go with the constant value, we can apply the table in the file, CSV file, square wave functions, sine functions also available. Okay, and polynomial type of the fitting. So few options is available. So if you are able to map your requirement with this, then go ahead, otherwise we have to code that conditions. Okay, so here we have a certain class of derived conditions that I want to show you. So that few conditions we derive based on the fixed value options. Okay, so fixed value is our primitive type, and from that primitive type we are deriving certain class of mu conditions. Okay, so moving wall velocity, pressure inlet outlet conditions. Okay, pressure Dirichlet inlet conditions. Then we have surface normal fixed value, total pressure, turbulent inlet. Okay, so this turbulent inlet condition sometime we going to use for the turbulent LES type of calculation, when we want to specify certain inbuilt random perturbation on certain component of velocity or pressure or temperature at that point of time. This turbulent class of condition is very useful. Then the sum condition is based on the fixed gradient or zero gradient. Okay, like flux corrected velocity, buoyant pressure. Okay, so this few entries is also available. Then some mixed type of inlet outlet inlet condition, pressure inlet outlet velocity, pressure Dirichlet type of conditions, pressure transmissive supersonic free stream. Okay, other is the slip condition. So sometime we require the slip conditions. Okay, so zero gradient if phi is scalar, if phi is vector, normal component is fixed value 0 and tangential component are zero gradient. Okay, so normal component is on that particular patch is fixed 0 value. So let's say we talking about the flow through a channel, and we talk about slip condition on the top wall. So normal component on that particular top wall is y component, so y equal to 0, and tangential component with the top wall goes as a u component, so that gradient of u component goes as a 0 if it is 2D. Okay, so like that way you can check the different condition with the help of the slip conditions. Okay, partial slip, mixed zero gradient slip condition depending on the volume fraction. So this partial slip type of condition normally goes with something like a this interform type of calculation, VOF and all these calculations. Okay, so this is few of the derived class of conditions. Okay, so this is I gave you very quick idea about what different condition is available, but let's explore where exactly it is located, and if we go towards its actual location, you come to know various options as well. Okay, so normally let's say we want to explore exactly where this particular condition is available. So for that we supposed to go towards the area where we installed our OpenFOAM. So OpenFOAM, okay, OpenFOAM 3.0 SRC. Okay, in SRC go towards the finite volume. Inside the finite volume there is a field. Okay, inside the field we have FV patch. Okay, so look at this entire let's say detector structure. So let's go there. Okay, so that is the location where it is installed: OpenFOAM, SRC, finite volume field, and FV patch. Okay, so let's go to the base type of conditions. Okay, so we have this is all base type of conditions. Okay, zero gradient, mixed, fixed value, fixed gradient, coupled, basic symmetry, calculated. Okay, and if we go towards let's say constrained conditions, okay, so this is come under constrained conditions. Okay, so cyclic, symmetric, processor, wedge type, okay, empty, that all are constrained or pair type of the conditions. Okay, then we have a derived type of conditions. So if we go to a derived class of conditions, we have a huge options available. Okay, so let's explore couple of them. So derived class, normally we going to encounter couple of these entries, or we going to use few of these boundary conditions. Okay, so let's explore that. So this is, let's say we are talking about outlet inlet conditions. Okay, so outlet inlet is type name is outlet inlet. Okay, parallel let me open the inlet outlet, so you immediately come to know the difference. And inlet outlet conditions, okay, same H file. Okay, so here we have a inlet outlet conditions. So one is the outlet inlet and one is the inlet outlet. So what is the description about the outlet inlet? Okay, so boundary condition provide generic inflow conditions. Okay, let's go for inlet outlet. Okay, boundary condition provide generic outflow conditions. Okay, so when we talk about the inlet outlet, so it goes at a outlet condition. Outlet inlet normally goes as the inflow conditions, so it goes towards the inflow boundary, and inlet outlet goes toward the outlet type of conditions. So generic outlet with specific inflow for a specific case of return flow. Okay, so inlet outlet by default goes as the outflow conditions, but some reverse flow then it take into account. Here it's by default goes as inflow condition, but with specific outflow for a case of reverse flow. Okay, so this is how you can check, and this is the entry. Okay, outlet value, okay, if it is reverse flow, this goes. Inlet value, if the reverse flow, this goes. Okay, so like that way you can check. So sign conversion, positive flux out of the domain. So this phi, based on the phi, they try to check either it is inflow or outflow. That's why this entry is here. Okay, so if it is a positive flux, then apply the zero gradient conditions. Okay, negative flux, that means into the domain, apply the inlet value, fixed value. Okay, whatever the value you are giving, it's apply like that way. Same way here. Okay, positive flux out of the domain, apply the outflow fixed value. Okay, negative flux into the domain, apply the zero gradient condition, because it's by default generic inflow type of the conditions. Okay, so like that way you can specify or utilize these two very important conditions that is we regularly going to use. Another class of different class of conditions available is like a uniform total pressure conditions. Okay, so uniform total pressure condition, if you see, okay, so uniform description, boundary condition provide a time varying flow of a uniform total pressure boundary. Okay, time varying flow with a uniform total pressure conditions. Okay, so total pressure conditions, if you see, certain entries required: uniform total pressure, U value, phi, rho, psi. This is important when we talk about the compressible part. If it is incompressible, it is not material lot. So here you can see, wait, I will open C file. Okay, this is how it's coded inside. Okay, so if you are interested, you can check entire coding of that portion as well. Okay, same way uniform fixed value, okay, or uniform inlet outlet. Then we have a turbulent intensity kinetic energy. Okay, so turbulent intensity kinetic energy conditions we normally going to utilize. Okay, so this is how exactly you can calculate the turbulent kinetic energy. Okay, when you specify, so we going to specify the intensity based on the intensity and the velocity field name. Okay, whatever the name we required. So exactly the same way we able to calculate by our own Excel file as well. Okay, so either you go with this type of conditions and specify the turbulent intensity and the field variable name, okay, and they internally going to calculate the turbulent kinetic energy, okay. So that is another very important condition that you look at here. Then we have a free stream, okay, sometime we required, okay. Then we have another important condition is oscillating condition. I'm not able to find out. Oscillating fixed value conditions, okay. So sometime we require this oscillating fixed condition, oscillating condition in terms of amplitude and frequency, okay. And here is its equations, how it going to apply, okay. Its amplitude and frequency is here, okay, and some reference value with respect to that. If you want to do scaling, that is also possible. Patch offset value if required, you can utilize this. So this is oscillating type of conditions, okay. So let's say we want to specify the inflow as a oscillating with respect to time and certain frequency. This condition goes very nicely, okay. So reference value, if you put 0, it's quickly goes very nicely, okay. So certain very important conditions is readily available in the OpenFOAM area, okay. Hydrostatic pressure conditions, okay. Then yeah, so I suggest please try to walk through this all different class of conditions, okay. And you, let's say you required particular test case for so and so type of the conditions, okay. Then you have to go to our tutorial area, okay. So let me go towards that area, okay. Here is tutorial, and inside this use this command, okay, and try to find out if any of the tutorial is available that give you the idea about this oscillating fixed value. So yes, multi-phase flow potential free surface oscillating box type of one of the tutorial is available that give you the idea about this class of conditions. Let's say this turbulent intensity type of the test case you required, okay. Just type in this entire tutorial area, and so many options of the test case well set with this class of boundary condition you can come to know, okay. Let's say we required test case or the syntax. Normally we have to first identify the syntax that is going to match with our requirement. Let's say this inlet outlet, okay. So that condition is not used entirely in our distributed version of OpenFOAM test cases, okay. Let's say inlet outlet, but you're going to find couple of so many entries for this inlet outlet, okay. So it is a very important conditions, okay. So look, so many tutorial is set with this inlet outlet conditions. So like that way you can explore what different class of conditions is available inside this OpenFOAM area, okay. And along with that, I suggest try to read our user manual, okay. And in the user manual try to read the, let me give you exactly the chapter number, okay. So from there you can find out few more information about this boundary file, okay. So this 5.2 that give you the different idea about this boundary options available in the OpenFOAM, okay. So I suggest please go through this few concept and that give you the idea about different class of boundary condition is available. But bottom line is something like this way: whatever you specified, okay, this name must appear inside the 0th folder, all the name. Along with that, you're supposed to specify proper base type of conditions, and with that base type of condition apply the appropriate primitive or derived type of conditions on the 0th folder, okay. So that is how you exactly map one-to-one between base and primitive or base and numerical type of conditions inside the OpenFOAM, okay. So let's say you want to simulate certain class of your own test case, okay. So first identify what type supposed to be the boundary condition for particular your type of the case, okay. And then try to figure it out which particular tutorial give you the best match out of it. So adapt immediately from that portion, okay. And then you start when you start simulating, you come to know either this is appropriate or not, then accordingly you can change the conditions, and finally you get a appropriate or best match condition. Or you can if you exactly knowing what condition is appropriate for my type of calculation, then straight away go towards this entire go towards this entire this directory where exactly you find all the derived type of conditions. Okay, so go and try to fix or identify appropriate conditions. Okay, and then check either this condition is appropriate for me or not. Like fan. Okay, so let's say HVAC type of calculation is doing, so normally fan we cannot model or we cannot simulate the fan with the proper geometry, so it goes as a something like fan jump type of condition. This is a well proven conditions. Okay, and one can specify very quickly the fan type of concept inside the duct or any of the pipe or anywhere. Okay, so certain type of conditions you have to identify from this particular area, and I see that almost all type of conditions, whatever you see in the let's say established commercial solver, every condition is coded inside the OpenFOAM. Okay, so we need not to worry. But let's say even though with that also you're not able to simulate your own case, then we have to go towards our own boundary condition development. Let's say we want to specify the oscillating parabolic condition on the pipe. Okay, so that condition really not available, so either you go with groovy BC type of options where you use the groovy BC and try to create that condition, or you can code your own condition from the scratch. Okay, so we try to explore both the things when we move towards the advanced options. Okay, but this certain conditions is straight away available, so try to explore. Okay, and that is how you can going to learn multiple options that is available inside the OpenFOAM. Okay. So this is how you can explore different type of condition available inside the OpenFOAM.